Good afternoon, friends, and welcome again back to the another session of the physics. Today we are going to study the numericals of the magnetic effect of current and magnetism. So as you all are seeing here, today we will be dealing with the magnetic effects of the current and magnetism. And what I would suggest you, please, first of all, you should read the chapter of the magnetic effect of current and magnetism, which I have already uploaded. So first go through the theory part of this, get the concepts, write down the formulas of the chapter, and then only you can be doing the numericals of this particular chapter. Otherwise not, because you will not be able to understand. So it is my suggestion. So first of all, see the theory of the magnetic effect of current and magnetism, which I have already uploaded. Okay, then only you will be able to understand it properly. And as you all know, this is Parijat sir classes going on. So this is Parijat sir classes going on. So I would suggest, please, all of you to like, share and subscribe my channel so that I can get motivation to do more and more videos for you. So please like, share and subscribe the channel. Okay, so without wasting any time, let's further move on to the numericals of the magnetic effects of current and magnetism. Okay, so first numerical says a current of 5 ampere is flowing from south to north. So as you can see, the current is flowing from south to north. This is the current flowing, 5 ampere current is flowing south to north, straight wire. Find the magnetic field due to 1 centimeter piece. So here is a 1 centimeter piece of the wire. Here is a 1 centimeter piece of the wire. Okay, and I want it at a distance of 1 meter northeast, 1 meter away from this northeast. So as we all know, northeast means this is the wire is making 45 degree with the direction of the displacement vector. The wire is making 45 degree with the direction of the displacement vector. So already we have seen the formula. Please go through the theory so that you will be able to understand. The formula for finding magnetic field due to a straight wire carrying current at a distance of r is mu0 by 4 pi IDL sine theta by r square. This theta is 45 degree here. Theta is the angle made by the displacement vector and the wire. Okay, so let us put the values. Mu0 by 4 pi is actually 10 to the power minus 7, because already I told you in the theory mu0 is 4 pi into 10 to the power minus 7. So mu0 by 4 pi is 10 to the power minus 7. I is given to us. DL is 1 centimeter. We have to write it in meters. Sine 45 by r. R is 1 meter. This is r, 1 meter. So r square. So calculating it, we get this is the magnetic field in Tesla. This is Tesla, T for Tesla. And please watch one more important thing. What is the direction of this magnetic field? The direction of magnetic field is found out by Fleming's right hand rule. Fleming's right hand rule, which says that if the current is this, so if you put your thumb in this direction, the direction in which the fingers will curl, this is the current, this is current, and this is the magnetic field. So here we can tell that the magnetic field is actually going into the paper, which is cross. Into the paper. Cross means into the paper. So this tells that your magnetic field will be going into the paper. You have to hold it like this. This is current, and this is the magnetic field. So magnetic field at a distance of 1 meter is going into the paper, it is going into the paper, so vertically inwards. Clear? Next question. There is a current element dl whose value is given dxi. That means the current element dx is along the positive x-axis. The current element dl, as you can see here, this is the current element dl, is along the positive x-axis. This is along the positive x-axis, and the length of the element is given 1 centimeter. Placed at the origin, carries a current of 10 ampere. So this is the 10 ampere current. This is the 10 ampere current. What is the magnetic field on the y-axis at a distance of 0.5 meters? So from here, at a distance of 0.5 meter, what is the magnetic field at this point P? Okay, this is the current. This is the current flowing like this. Magnetic field at this point. Okay, so what is the formula? Formula is mu 0 by 4 pi ideal sine theta. So theta is the angle with the wire and the displacement vector, which is 90 degree here. Wire and the displacement vector, so the angle is 90 degree here. So we use sine 90. Okay, ideal, putting mu 0 by 4 pi 10 to the power minus 7. Current is giving 10 amperes. dl is given 1 centimeter, so 10 to the power minus 2, and distance is 0.5 meters, so 0.5 square. And so this is the magnetic field. And what is the direction of the, so this is the y-axis. Okay, and current is going like this along the x-axis. Okay, so current is going like this, so current will be up. Okay, the wire is this, current is going like this, so it is vertically up, vertically up. Okay, current, the current is going like this. Okay, this is the current going like this. So the current is going like this, x-axis. So the magnetic field is at a distance of this, at a distance of this is like this, like this, like this. So this is the current like this. Okay, that means it will be out of the paper. It will be out of the paper. So direction of magnetic field at P, direction of magnetic field at P will be out of the paper. That means it will be a dot here. Dot. Cross means going into the paper. Cross is into the paper and dot is perpendicularly out of the paper. Okay, so this is the direction of the magnetic field. It will be perpendicularly out of the paper, which is the z-axis. That is why it is written K. It is the z-axis. Okay, that is why it is written K. That means the magnetic field will be like this, like this. It will be along the z-axis. This is along the z-axis. That means K, along the K. Okay, this is the z-axis. Next, let us see. Here they have given, calculate the magnetic field at the center of a coil bent in the form of a square of side. So this is a square of side 10 centimeters and carrying current 10 amperes. So let the current flow in this direction. This is the flow of the current. This is the flow of the current. This is the flow of the current, and this is the flow of the current. This is the flow of the current. Okay, this is the current 10 centimeter side. So the question is, what is the magnetic field at the center? So let us first calculate AC. So AC will be what? AB square plus BC square, which is 10 root 2. Okay, so what is OC? OC is half of 10 root 2, which is 5 root 2. And what is PC? So OC, as you can see, OC is coming as 5 root 2. So what will be OP? OP is OC square minus PC square. So we can calculate it and we are getting 5 centimeter. So OP is 5 centimeter. Clear? OP is 5 centimeters. So now let's see. So OP is 5 means OQ is 5, OR is 5, OS is 5, OP is 5. because all these are of same length. They are of 5 centimeter each. Okay, these are all 5 centimeter, 5 centimeter, 5 centimeter and 5 centimeter. Clear? Okay, so now let us calculate what is the magnetic field at O due to BC, due to BC. So as you can see in BC, okay, so B is subtending, the point B is subtending an angle of 45 degree at the center. Point C is subtending an angle of 45 degree at the center. Okay, so the formula for a straight wire carrying current to produce a magnetic field at a given point, this is the formula. So you have to remember this formula, and so according to this formula, please see, it's mu 0 by I, mu 0 I by 4 pi r. Okay, what is r? R is actually OP. R is actually OP. Sine phi 1 plus sine phi 2. What is phi 1 and phi 2? Phi 1 and phi 2 are the angles subtended by the end points of the wire B and C at the center, which is 45 and 45. So here we are doing this calculation, putting the value of mu 0, I and r. Okay, this is r. Mu 0 by 4 pi is 10 to the power minus 7. I sine 45 and sine 45, and on calculating this we are getting, this is the magnetic field at the center due to the wire BC. And if I apply Fleming's right hand rule, so see, the current is going in BC, current is going like this. So magnetic field will be vertically down. Magnetic field is vertically down into the paper. Okay. So this is the magnetic field. Similarly, see, if I want to find due to AB, so what is the magnetic field? The value will be same, and in AB the current is going like this. In AB, see, the current is going like this, so it will be vertically up. It will be vertically up. The current is going like this, so it will be vertically up in AB. Okay. So no, it is vertically down. It is vertically down because I can't show it to you. So it is like this, vertically down. Current is going like this, vertically down. So vertically down. Okay. So this is vertically down. Similarly, due to AD, so in AD current is going like this, so vertically down at the center. In AD current is going up, so vertically down. Okay, AD. And in CD current is going like this, so vertically down again. That means all the magnitudes are same and all the directions are same. So total magnetic field at O will be all added up, which is 4 times of this value. So this is the magnetic field at the center, 4 times of the magnetic value. Okay, so this is the magnetic field at the center. Next, let us see two semi-infinitely. Semi-infinitely means, see, this is a wire which is infinitely extending here, and again this is a wire which is infinitely extending on one side. That is called semi-infinitely. Okay, one end of them is common if both the conductors carry the current I. So both of them are carrying current I and I. As you can see that, find the magnetic field at the point this. So this is my A and this is my B. So now for a semi-infinitely, please watch this angle, this point, okay, at a distance of B. So the two ends of this point is, one is here and the one is infinite, so that will make 90 degree. One will make theta 1 and one is making 90 degrees. Similarly, For this wire, one is making theta 2 and the one which is infinite will make 90 degree. Okay, so and this distance for this wire, the distance is B, for this wire the distance is A. So watch here, magnetic field at P due to OY, this is the OY, this is the OY wire, so which is mu 0 I by 4 pi A. A is the distance of the point P from the wire. Okay, sine theta 2, it is making one point, is at one end it's making theta 2 and the other end it's making 90 degree. So sine 90 is 1. So this is the magnetic field, and if I apply, current is going up, if I apply, it is vertically downwards. Similarly, magnetic field at PAB due to OX, which is at a distance of B, P is at a distance of B from the wire. One end is making theta 1, the other end is making pi by 2. So this comes, and again current is going like this, so vertically downwards, vertically downwards. So since both are vertically downwards, so the net magnetic field will be at B. Total magnetic field at P will be added up. So taking the common parts, we are getting this. Now sine theta 1, as you can see, sine theta 1 and sine theta 2 values, we can easily find it out. It is the perpendicular, theta 1 is perpendicular by the hypotenuse, as you can see here. Putting the values of sine theta 1 and theta 2, this is the magnetic field at the center. Okay, next, now current flowing in 3 wires, as you can see the 3 wires are X, Y and Z axis. The currents flowing are I and I, and all the 3 wires are perpendicular to each other. As you can see, they are all perpendicular to each other. Question is, what is the magnetic field at this point? 0, 0 minus A means it is on the negative side of the Z axis. This is R 0, 0 minus A. Okay, so you have to find what is the magnetic field due to the X axis current, Y axis current, Z axis current. Now due to the X axis current, as we can already see from here, okay, it is at a distance of A. So we can write mu 0 I by 2 pi A. This is the current flowing due to the whole wire, at a distance A from the center. Okay. Similarly, from Y also it is at a distance of A, and from X also it is at a distance of A. Okay, so and due to the Z it will be 0 because it is lying on the axis. Due to the Z axis, current is flowing along the Z axis, so point is on the Z axis, so the magnetic field at P due to the current in Y axis, Z axis, will be 0. So what is the resultant magnetic field? It is Bx square plus By square root. So putting the values, this is the current and what is the magnetic field? So let us see. The magnetic field due to the Y axis, okay, current is going up, so magnetic field due to Y axis will be, the magnetic field due to the Y axis, the current is going up, will be along this, okay, so this you can see, and magnetic field due to the X axis will be along, this is the current, so along down, so this is the magnetic field along the X axis. So what is the, so they are inclined at perpendicular to each other, so resultant magnetic field is using this formula, will be along the XY plane, that means XY dash, so this, the resultant magnetic field will be along this axis, this part, this section. Clear? Let's see, a straight wire carrying current of 12 ampere is bent into a semicircular arc of radius 2 centimeter. Now they are telling what is the magnetic field at the center of the arc. Consider the magnetic field B at the center of the arc. So it's a semicircular with a radius given, current carrying is also given. Okay, so what is the magnetic field due to the straight segments? So let's see, this is the straight segment, this is the straight segment. So magnetic field due to the straight segment at a point on the line will be 0. Please keep in mind, magnetic field on the line due to a current carrying wire is always 0. So magnetic field at O due to the wire AB and DE will be 0. Okay, because sine 0 and sine 180 is 0. So using this formula we can see that the sine phi 1 and sine phi 2 both will be 0. Okay, so since the sine angles components are 0, so magnetic field due to the straight wires at the point O will be 0. Similarly, magnetic field due to the semicircular ends at the center here, okay, due to the semicircular end carrying current like this. So semicircular end, which is this formula, magnetic field due to the whole circle at the center, magnetic field due to a circular wire at the center is given as mu 0 I by 2r. So due to the half circle it will be half, which is this. And since it's clockwise, please note here, the magnetic field will be perpendicularly into the paper, so it will be a cross. Cross means into the paper. Cross is into the paper, dot is perpendicularly out of the paper. Now the magnetic field due to a circular wire carrying current at the center is given as this and is also directed perpendicularly, so into the paper, so it will be into the paper. Now the question is, the next part was, they are telling that would your answer be different if the wire were bent into the semicircle arc of same radius but in opposite way. So watch here, that means if I bend it like this in the opposite way, will there be any change in the magnetic field? There will be no change in the magnetic field, but its direction will be just opposite, because all the values are same, but its direction of the magnetic field will be different, it will be reversed. Okay, because current now here is flowing anti-clockwise, and anti-clockwise means the current which will be direction of magnetic field will be into the paper, perpendicularly into the paper. Okay, it will be perpendicularly out of the paper, so everything will remain same, but the direction of the magnetic field would be reversed. Next, a tightly wound 100 turns, so number of turns is 100, radius given 10 centimeter, current given 1 ampere. What is the magnitude of the magnetic field at the center of the coil? We all know magnetic field due to a circular wire at the center is given by this formula, into n. N is the number of turns, mu 0 I by 2r into n. So putting the values, we get the magnetic field at the center. Similarly, the electron in a hydrogen atom circles around the proton. The speed of the electron is given to us. Orbit radius is given to us. Okay. equivalent current. Now we are telling that what is the current. As you know, current is I equal to Q by T. Q equal to, here one electron is revolving, so E. And time period, what is the time period? It is making a circular path of radius r. Here is the electron. Okay, so distance covered is 2 pi r by the velocity will give me the time period. So using this time period, we know the velocity, we know the radius, we know the electron's charge. Putting all the values, we are getting this will be the current produced in the when an electron is revolving around the proton in an hydrogen atom. So what is the magnetic field at the center? We know this is the formula. Now we know the value of I, we know the radius of the loop. So mu 0 is 4 pi into 10 to the power minus 7. I, the value of the current is given to us, we found just now, and it is 2r. R, this is our R. So we get the magnetic field at the center. Next is, friends, look here. There is a loop PQRS P. This is a semicircular loop shown here. Okay, the radiuses are given R1 and R2. They are carrying currents the same. Find the magnetic field at the center. Please watch here. Magnetic field due to the, how many parts are there? One is due to the straight wires. This and this at C will be 0. Will be 0 because the point lies on the line of the wire. So magnetic field due to the straight wires at the center, 0. Next, what is the magnetic field due to the part R? It is R, okay, SP, sorry, SP, okay, this bigger semicircular wire. The magnetic field due to the bigger semicircular wire, whose radius is R2, is given as this. Okay, we know for a whole circle the magnetic field is this, so for the semicircle it will be half of this, which is this. Now what is the current flowing in that bigger semicircle clockwise? So magnetic field at the center will be going into the paper. Similarly, magnetic field due to the smaller radius R2 at C will be this, and here current is coming anti-clockwise. So magnetic field at the center will be coming out of the paper. Now we see that R1 is less than R2. So magnetic field, this part is greater than this part. Okay, so the net magnetic field will be subtraction of these two, and because this is upward, so the net resultant magnetic field will be upward. Clear? Okay friends, so let's see. A long horizontal conductor is bent and a current I, this is a wire, straight wire and a circle in the form of radius R carrying current I and I. So question is, what is the magnetic field at the center? So due to the straight wire, the distance of the center is R. So magnetic field due to a straight wire, we all know, is this, and the direction of this will be the perpendicularly into the paper. So here perpendicularly into the paper, direction of magnetic field. Similarly, due to the circular wire, the magnetic field is given as this, and because it is clockwise current, so it should be into the paper. It should also be into the paper. Magnetic field due to the straight wire will be perpendicularly out of the paper. If we apply the direction, if we apply the direction, so please watch here, magnetic field due to the straight wire will be, this is the magnetic field upwards, okay. So this will be due to the straight wire, it will be upwards, yes, and due to the circular wire clockwise it is downwards. So the net magnetic field will be subtraction of these two, okay, and because this is bigger, B1 is bigger, so the net direction of the magnetic field is downwards. Similarly, as we can see here, there is a coil of 120 turns, radius given 18 centimeter, current flowing is 3 ampere. What is the magnetic field at the center? So at the center the magnetic field formula is this, having n turns. So putting this is the value of the magnetic field due to the circular wire having 120 turns, this is 120. Now they are telling at a point on the axis of the coil at a distance, so they want that on the axis at a distance of equal to the radius. So here along the axis which is perpendicular to the plane of the coil, as you can see, this is the coil, this is the coil, okay, and it is carrying current, it is carrying current I. So what is the magnetic field at this point, which is equal to the radius of the wire, okay. So using this formula, please watch here, magnetic field at an axis at a distance of r is this, okay. So here we know that calculations, this is 2r square to the power, it is 2 to the power 3 by 2, so this is r square to the power 3 by 2. So calculating and putting the values, we get that the magnetic field is this, which will be along the axis, along the axis of the wire, the magnetic field direction will be along the axis of the wire. Clear? Okay friends, so let's see. There is a circular segment, as you can see, of radius 10 centimeter, subtending at an angle of 60 degree. What is the magnetic field due to? The current carrying is 9 ampere current is flowing like this. So what is the magnetic field at? So due to the straight wire, due to this wire and this wire, because the point lies on the line of the wire, so magnetic field due to the straight wire CO and BO is 0, okay. Now we have to find out what is the magnetic field due to the only the segmental arc CD at O, okay. So it is mu 0 I by 2r, the angle subtended by 2 pi. Please note here, note the formula, it is the angle subtended by the segment by 2 pi. This is the formula, okay, which is coming this. Putting the value of I, mu 0 is 4 pi 10 to the power minus 7, and r, we get the magnetic field at this. Now because it is clockwise, the current flowing is clockwise, so it will be perpendicularly into the paper, it is into the paper, perpendicularly into the paper. Clear? Okay friends, so next see, two wires A and B. So here we have got two wires A and B of length 44 centimeters and carry a current of 10 amperes each. Both the wires carry current 10 amperes each. Wire A, you are bending it into a circle, so we can tell that 2 pi r equal to 44. From here we can find out the r, radius of the wire. and wire B is bent into a square. Okay, so for the wire B, 44 will be 4 into side, so side will be 11 centimeter. Now the question is, which wire produces a greater magnetic field at the center? So let's see. Wire A is a circle of radius r, so magnetic field at the center, we know the formula, mu 0 I by 2r. So this is the magnetic field due to the circular wire A at the center. Now for the wire B, as you can see that all these lengths are 11 centimeters each. 11 centimeters each. So this part, as you can see, this part is subtending an angle 45 degree, and this part is also subtending angle 45 degree at the center. Okay, and this is carrying current. Clear? So now let us use the formula mu 0 I by 4 pi r. What is r? R is On. R is On. So how do we get On? We apply cos 45 is On by OP. As you can see, this is my OP, which is L by root 2. This is L by root 2. Okay, so On, cos 45 is base by the hypotenuse. So On by OP. So from there we get OP as 11, On as 11 by 2. We get On as 11 by 2. Okay, so this is the formula mu 0 I by 4 pi into On. Sin 45 plus sin 45, On's value all I know. So this is the magnetic field due to a single wire. So magnetic field due to the 4 wires will be 4 times of this. Magnetic field due to 4 wires will be into 4 times of this, which will come out to be this. So now we can see that the magnetic field due to the square is more. Magnetic field due to the square is much more than the magnetic field due to the circle at the center. Magnetic field due to the square is more than the magnetic field due to the circle at the center. Clear? Two wires carry current of 10 amperes each. So these are the wires. So this is carrying current 10 amperes. This is carrying current 10 amperes, and here is the current flowing, which is 10 ampere current. Okay, so what is the magnetic field at the center? So first of all, due to the straight wires, the magnetic field at the center should be 0. So what is the magnetic field due to only this segment, circular segment? If this is 90, so this will be 270, which is 3 pi by 2. So already I told you magnetic field due to the circular segment is mu 0 by 2 r, mu 0 I by 2 r, angle subtended by 2 pi. So calculating this, we get this, and because it is clockwise, so magnetic field will be perpendicularly into the paper. Perpendicularly into the magnetic field is perpendicularly into the paper. Okay, friends, next see one more. So as you can see here that this is a long straight wire of radius A carrying current I. The current I is uniformly distributed. Okay, so watch here please. You have to find what is the magnetic field inside the wire at a distance of r, which is less than A, and outside the wire at a distance of r, which is greater than A. So two parts we have to make. They are telling that the wire, that the current is actually uniformly distributed over this. The current is actually uniformly distributed in this whole wire. Uniform distribution, because it's a thick wire, so current flows uniformly over this wire. That means I can take it like this, कि for the whole cross section, okay, which is pi a square, the current is I. So for only this cross section, which we are taking as R, okay, so current will be this. For the whole cross section pi a square, current is I. So for the cross section pi r square, the current should be this much, which is this. So this is the current flowing only in that section of radius r. Clear? Next is, let us imagine an Amperian loop of that radius. So according to Ampere's circuital law, according to the Ampere's circuital law, what can we write? Line integral of B dot dl equal to mu 0 I dash. As you know that the Ampere's circuital law says that line integral of B dot dl equal to mu 0 into the I. I is the current flowing through that whole section. dl is the length of the section. B is the magnetic field. Okay. So B goes out, integration of dl. So I is the current, I dash is the current only in that portion, only in this portion, because over a radius r, how much is the current flowing? It is only this much. So we will take, instead of this, I will take this current, and integration of dl, total length is 2 pi r. So from here we get the magnetic field at the center due to the wire which is of radius r less than a will be this much. Next, for a distance which is more than the radius, r greater than the a, r is greater than a, that means we are taking a point which is outside the thing, this part, okay, outside. So for this, as you can see, we have to take the whole wire, so the total current should be counted here. So line integration of B dot dl, dl is 2 pi r mu 0 I. So this is the magnetic field, due at a distance of r which is greater than the radius of the wire. This is the magnetic field at a distance of r which is greater than the wire. Clear? Next, this is a straight wire, straight solid conductor. Please watch here, solid conductor of radius 5 centimeter carrying a current of 3 ampere, uniformly distributed over its circular. That means the full current is uniformly distributed. The full current is uniformly distributed in the whole wire. Okay. So if we now see this, they are telling what is the magnetic field at a distance of 4 centimeter. See, the wire is of radius 5 centimeter and they are asking at a distance of 4. That means this is 4. This is 4 centimeters. So definitely current in this region will be less. So how to find out? Current only in that portion is this. Because current in the whole pi r square, the current is I. So therefore in the region pi r square, the current will be this, which is this. So again, using Ampere's circuital law, because it is inside the medium, so relative permeability of the medium should come. Relative permeability of the medium with what it is made up of should also come. Okay, so dl will be 2 pi r. Now putting the values, we get this is the magnetic field, and now putting the values what we know. Relative permeability mu r is given 1000. This is mu r, this is mu 0. Okay, this is the current I, this is the distance at what, 4 centimeters. 2 pi r is the total radius. We get this is the magnetic field produced inside the wire at a distance of 4 centimeter. A solenoid of length 0.5 meter and radius 1 centimeter is made 500 turns. So length of the solenoid, this is a solenoid as you all know. The length is given 0.5 meter. The radius of the wire is given as 1 centimeter, and there are 500 turns. It carries a current of 5 ampere. What is the magnitude of the magnetic field inside the solenoid? So as we know, magnetic field due to solenoid is this formula, mu 0 Ni. N is what? Number of turns per length. So this is 500 in a length of 0.5 meter. Mu 0, and this is the I. So calculating it, we get this is the magnetic field due to the solenoid. Next is a solenoid of length 50 centimeter and 1000 turns, carries current 2.5. What is the magnetic field at the interior? So at the interior, this is the formula. Mu 0 is 4 pi 10 to the power minus 7. N number of turns per centimeter, 1000 by 0.5, and this is the I. So this is the magnetic field due to the at the interior of the solenoid. At one end, that means at either this end or this end, it will be half of this. So putting the value, half of this is this. A toroid, this is the toroid, as you can see, this is the toroid, okay, having number of turns here like this. It is a toroid. Inner radius 20 centimeter, outer radius 22 centimeter. 4200 turns of wire are there, and current flowing in the wire is 10 amperes. What is the magnetic field inside the core of the toroid? First of all, the mean radius of the toroid will be this. Now it is just acting the total length of the toroid, 2 pi r dash, which is this, and in this length you have total 4200 meter turns, 4200 turns over a length of 132. So number of turns per centimeter per meter is this. Now magnetic field inside the toroid is same as the solenoid. We are calculating it, we are getting this. Outside should be 0. In the empty space, that means this area, it should be 0, because magnetic field is only in the conducting part of the toroid, conducting part, these parts, only in these parts. Clear? Next, see BCDF circular wire, and BA is a straight wire and DA is a straight wire carrying current 5 ampere. So what is the magnetic field? And they have given that the radius of the diameter is 10 centimeters, so the radius is 5 centimeter. Okay, so what, this is 5. So first of all, the magnetic field at O due to the wire AB and DE. Okay, so AB and DE will be this formula we have done, straight wire. One end is infinite, this is infinite length, infinite length. So only at one end is sine 90 plus sine 0. So this is due to the straight wire. Okay, and using the concept of the Fleming's rule, we see that they are perpendicularly upwards due to the two straight wires. Now there are two sections of the circular part. As you can see, this is one section and this is the other section. So please watch here. Here current is going anti-clockwise and here current is going clockwise at the center. So total magnetic field due to the circular wire will be cancelling each other. So the net magnetic field at the center will be only due to the two straight wires, which is this. Okay, it is only due to the straight wires. Next is, there are two very long wires, that means infinite at one end. So moment I give infinite at one end, you have to put sine 90 and sine 0. Okay, sine 90 and sine 0. So we have to find out what is the magnetic field at the point P at a distance of 35 centimeter from it. So due to the wire OY at P, so first this angle is 90 and the other angle will be 0 degree. So using this formula, so calculating it, we get this is the magnetic field due to the OY along B2, due to this B2, and due to this wire it is along B1. Again it will be a sine pi by 2 plus sine 0. Current is, and the direction will be in this direction. So the resultant will be this. And this is the resultant magnetic field due to the infinite wires, okay, at a distance of 35 centimeters from the point O. Clear? This is how we calculate the magnetic field due to the different type of combinations. So I would suggest you please go through these numericals very carefully, and then you have to spend some time and formula, but before that please go through the theory part which I have already uploaded. So it's my request, without theory please do not try to attempt these sums because it will be tough for you. Okay, so it's over for today, and thank you so much for attending the class, and my suggestion is please keep watching Parijat sir classes. Please keep watching Parijat sir classes. Okay, and I would suggest you that please go and subscribe the channel for me so that I get more and more motivation to make more videos for you. Okay, so till then it's goodbye from my side, and thank you so much for attending the class. Thanks a lot.